Welcome back. Let us continue. Okay. We have started looking at mass flux. We started looking at mass flux in the previous class. We looked at some formulations for the flux itself in terms of rather fundamental quantities, density, velocity, concentration, and so on and so forth. And let us take things further. In this class, we are going to look at something called a shell balances approach to mass flux to get useful aspects from that analysis. Generally speaking, there are two approaches to solve these problems, the problems that involve motion of various substances and so on and so forth, which are plenty in engineering practice. There are two broad approaches. First is called the shell balance approach, and second is called the application of the relevant conservation equation directly. Let us look at both of them. Both of them have good merit. Let us look at them and then I will talk about them. The relevant conservation equation is nothing but the equation of continuity in the case of mass conservation. That is the only thing that we have seen so far, and so I am going to look at that. But first we will look at the shell balance approach. What are shell balances? Okay. Look at the term, things will start falling into place. Shell balances. Balances of conserved quantities are made over a representative shell in the system. Those are called shell balances. This representative shell, what is that? The shell represents the geometry under consideration. For rectangular Cartesian coordinate systems, the shell could be a cuboid. Okay. We will see this in detail next. For cylindrical systems, the shell is an annular cylinder. You have a cylindrical system, you are going to use cylindrical set of coordinates. So, the shell over which you are going to do your balances is going to be an annular cylinder. And for spherical coordinates, the shell could be an annular sphere. Okay, spherical coordinates, annular sphere. So, we essentially that is the space over which we do balances, and that space is differential, and therefore, the variations are captured nicely when you do balances over that shell, and then when you integrate you get the entire picture. It is as simple as that. This will become clearer if the concept of a shell is not very clear. Do not worry about it, it will become clearer as we go along. Now, we are going to consider a uniform membrane. Okay, we will directly jump into systems of relevance to us, a uniform membrane. In that membrane, let us consider a shell of thickness delta x through which diffusion occurs normal to the surface area. This is the membrane, okay, indicated by these thick lines. This is the membrane of thickness L, and the area is perpendicular to the plane of the motion of the species. Okay. So, the area is somewhere here. We are going to consider a shell because this is to begin with a cuboid, right. I have just drawn 2 dimensions here. You could extend the 3rd dimension and consider it a cuboid. You take a thin shell of thickness delta x. So, that is represented as x here and x plus delta x here. This is very thin. I have just expanded the delta x to show you, so that you can see it. In reality, the delta x is very small, and in 3 dimensions this is going to be a cuboid of the same dimensions as that of the system or the membrane, but with a thin thickness, or the thickness is very small. So, that is essentially the shell, and we are going to do balances over the shell, mass balances over the shell. That becomes a system. So, our mass conservation equation, as you all know, which can be used blindly, is dm dt is input rate minus output rate plus generation rate minus consumption rate. you could consider both these together and call it the net production rate, R generation minus R consumption, as some sort of a net production rate. Now, a material balance, if you write over the shell on the component I, which is entering at x and leaving at x plus delta x. Okay. So, here is the shell, you have x here, x plus delta x here, the component I is entering in this direction at x and leaving at x plus delta x. Okay. That is the situation here. So, if you consider that, in terms of the molar fluxes of I, we could write this d dt of m. So, d dou t, since it could vary with time and space, I have just given the more general partial derivative here, it does not matter. Dou t of the mass is concentration times the molecular mass or molecular weight. Okay. Concentration is moles per volume. Moles into the molecular mass will give you the total mass over volume, and if you multiply that by the volume of the system, A times the delta x, it is a cuboid, therefore, A times the delta x, that is the volume of the system. So, this becomes the mass of species I equals the molar flux of species I at x times the molecular mass, that will give you the mass, but this will be per unit volume, and molar flux, and this is the area here. If you multiply it by the area, this becomes the flux, the molar flux, the mass flux, and mass flux times the area will give you the mass rate, and that is the reason for this combination Ni at x, molecular mass I times A, minus the output rate. The output is at x plus delta x. So, Ni at x plus delta x, molecular mass output times the area, the rate, this is the flux and you get the rate, and Rg minus Rc in the regular reaction rate terms is Ri. This is in terms of moles, typically we write it in terms of moles, our reaction rates. Therefore, we need to multiply it by the molecular mass times the volume, because this rate is normalized with respect to volume, and therefore, we need to multiply it by the volume to get mass per time. Okay. The idea here is to get mass per time for each of these terms, and therefore, we took whatever we had, concentration per time, and we converted that into mass per time by multiplying by the molecular mass and the volume here. Here we had a flux, the molar flux, we converted it into mass flux first and then mass rate, and then similar thing that we did here. Here we did the reaction rate, which is in terms of the concentration on a volumetric basis, multiplied by the molecular mass to get mass on a volumetric basis. Then we multiplied it by the volume of the system, A times the delta x, a cuboidal volume, so that each of these terms is mass per time. That is the whole point, and that is what we normally do when we write balances. Make a note of that. This is equation 2.3.1-1. Now, if we divide throughout by molecular mass times A is a constant, molecular mass of the species I is also a constant. So, you can divide throughout. Can you divide throughout and tell me what you get? Pause the video here, come back after you get the expression, then we will continue. Go ahead, please. If you divide it by the molecular mass times A, this goes away here, these are constants, therefore, you get dou Ci dou T, and this we have a delta x here, we will keep this here for the time being. Ni divided by molecular mass times A, this goes, Ni at x remains here, and minus Ni at x plus delta x remains, and Ri delta x remains. And now, if you divide by delta x throughout, here you are left with dou Ci dou T, here you are left with Nix minus Nix plus delta x divided by delta x. Do you recall something familiar here? You soon will, I gave you a hint, plus of course only Ri remains here. Okay. This, if you recall, is nothing but the definition of a derivative when the limit of delta x tending to 0 is taken. If you do that, we get, go ahead please, pause, do that and get back. If you do that, you get dou Ci dou t equals minus, because the definition of the derivative is x plus delta x minus x divided by delta x. Here you have just the negative of that, therefore minus dou x of Ni plus Ri. Okay. We will call this equation 2.3.1-2. Here the flux is purely diffusive. It is just diffusing. Okay. There is no other driving force that is causing this motion. Therefore, Ni is nothing but Ji star, only the molar flux, and we have an expression for molar flux in terms of Fick's first law. Molar flux is minus di dou Ci dou x. Strictly speaking, it is di minus of dou Ci dou x, but that we, by writing this, we understand what we mean, minus di dou Ci dou x. Therefore, dou Ci dou t equals di dou squared Ci dou x squared. You already have a derivative, and then you have a derivative here, dou Ni dou x, right, and Ni itself is a derivative dou Ci dou x, and therefore you have di dou squared Ci dou x squared, negative negative will cancel out, plus Ri. We will call this equation 2.3.1-3. If there is no net production of I in the volume is again A times delta x, this is the shell, by a reaction, then you can put Ri equals 0. If you do that, that term disappears and you get dou Ci dou t is di dou squared Ci by dou x squared. We will call this 2.3.1-4, and this is Fick's second law. Fick's first law is the constitutive equation, the relationship between mass flux and the concentration gradient. This, the variation of concentration with time on this side and the variation of concentration with space on this side. So, that way it is very powerful. Variation with time is related to variation in space through this diffusion coefficient or diffusivity di. Under steady state conditions, okay, you know what steady state is, the properties of interest at a point do not vary with time, which means effectively any time derivative goes to 0. So, this time derivative goes to 0, and what do you get? Pause, do that and get back. Yeah, you would get 0 is di dou squared Ci by dou x squared. Okay. Very simple, beautiful expression, di dou squared Ci dou x squared equals 0. And this is equation 2.3.1-5. In 3 dimensions, we looked at 1 dimension to get a physical feel of things. We can extend this very easily to 3 dimensions. It is going to be dou Ci dou t equals 0 equals di times del squared Ci, dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared Ci. Okay. So, 3 dimensional variation is brought in here. So, this is Fick's second law in 3 dimensions, equation 2.3.1-6. Okay. So, we will stop here. We have covered quite a bit of new information here, constitutive equation, Fick's first law as an example. Then we looked at, that was the previous class. In this class, we looked at shell balances, and shell balances we wrote for a membrane, a thin representative shell, which turns out to be a cuboidal shell in a membrane. And then we derived the Fick's second law, which is a relationship between the time variation of concentration and the space variation of concentration in the system. Okay. We'll continue in the next class. See you in the next class.